everyone, today we will be covering the Wav2Vec architecture and just go through a review of the paper because we will be implementing this entire setup in the future. It's relatively complicated actually, so it'll be good just to take a look at the paper, understand some of the details right now, and then we'll reference back to this when we actually get to the implementation. So Wav2Vec is a self-supervised way of learning speech representations, and it does it in a really cool way. So what we're going to do first is just understand what are some applications of Wav2Vec and then build from there. So one of the most common applications of Wav2Vec will be for automatic speech recognition. So we actually looked at a speech recognition model, an ASR model, called deep speech earlier. So I will go ahead and post that video down below. There's going to be actually a lot of prerequisites going to building Wav2Vec. So hopefully you understand deep speech, but the main idea behind deep speech is we have some audio. We then convert it to a MEL spectrogram, right? So MEL spectrogram. This goes into a neural network that's full of convolutions plus some recurrent layers, LSTMs. And then we use the CTC loss, right? CTC loss to predict the transcript, right? Let's say it's hello world. So in this pipeline, if there's anything you're unfamiliar about, I have a video on CTC. I have a video on producing, working with audio data to produce things like MEL spectrograms and things like that. And I have another video implementing the entirety of the deep speech to architecture. So you can see all of this and how it comes together. And so I'd recommend you go do that first if you're confused about anything here. So now we have this, but what did we train this on? This was trained on 960 hours of LibreSpeech data, 960 hours of LibreSpeech data. And LibreSpeech is basically an audiobook data set or something like that we have some audio, right? And we have its transcripts, right? We have audio and transcripts. So we have the input, the audio, we have the output, the transcripts. And so it's a supervised problem. We have the input and the output. We train a neural network to map one to the other. Nothing too crazy. But speech recognizers require a lot of data to get state-of-the-art results. And 960 hours is honestly the bare minimum to get a good speech recognizer on supervised learning. So if you start with a completely randomly initialized model and train it from scratch, this is kind of bottom of the barrel here. So what do we do to train neural networks on smaller data sets? Well, first we have to kind of come up with some ideas. Why do we care about training neural networks on smaller data sets? What are some applications of speech on smaller data sets? And these are some of the problems that I personally work on, right? So we have disability speech, right? Disability speech, right? If you have some type of vocal disability, something like that, can we have speech recognizers still understand you? There's accented speech, right? If you have an accent that's not like the ones that's typically kind of in your LibreSpeech data set or kind of that North American, where most data sets come from, they come from like North American speakers. If you don't have that accent, then these speech recognizers probably won't work for you. And when it comes to these data sets, there are data sets for accent, there are some data sets for disability. They are not even in the hundreds of hours, they are in the maybe 10-hour range, 10 to maybe 50 hours at the most. So very, very tiny data sets to train on. And that's not enough to train a speech recognizer. So how have we done most neural network stuff for small data sets these days? We do transfer learning, right? Train on we have a big data set, right? We have a big data. We have a big data set of stuff, and we train our neural network on this. And then we have a tiny little data set of our target, right? Tiny little data set that we fine tune our model on. That's our standard setup for most kind of training methods these days. It's just, if we have lots of data, think about how much data we have. We actually have a pretty good amount of data of audio that's been transcribed, right? Between Common Voice and LibreSpeech and all the other kind of data sets out there, we probably have close to maybe 10, 20, 50,000 hours. Actually, we probably have more than that. We've close to like a couple 100,000 hours of audio. That's been nicely transcribed for us to train speech recognizers, no problem. But in our big data, only a little bit of it, right, is labeled. So this labeled region could be, a couple 100,000 hours worth of labeled audio, but there's millions or tens of millions or hundreds of millions of hours of audio that is unlabeled, just raw audio. And this includes things like YouTube videos and podcasts and music and anything else, right? So we have lots and lots and lots of audio on the internet, but it's not labeled. We have no transcription for them. We just have audio. So the question is, can we leverage this audio? And of course we can. In the same way, when we say that we train a model like GPT with causal language modeling or BERT with mass language modeling on lots and lots of text, it's done through corrupting the data and then predicting the thing that was messed up. So let's kind of talk about BERT. So mass language modeling looks like this. You have BERT. You pass in some tokens, token 1, token 2, a mask, token 4, and we know this should be some token 3, right? We know what the original data was. We just replace one token with a mask token. And then the neural network's goal is to predict, what is it? And we know the target, this should be token 3. No problem there, right? Because language is already discretized through tokenization, this is a relatively straightforward setup, right? Obvious setup. Now, what about for audio? So audio, we have some audio. We'll use some convolution. Let's say we're just directly working with the waveform, so we can use a convolution set, right? So convolution, we're going to extract some features from the audio, right? Some sequence of embeddings from the audio. So we take this audio, we extracted some features from it, and now what we have is a transformer, right? So or LSTM, it doesn't really matter, transformer, and we're going to again predict a sequence of outputs on the other end. Now, let's say I do the masking right here. So I mask out this part of the audio. Well, let's say I can do the math and figure out if I mask out this portion of the audio, then that maybe refers to these embeddings right here. And so our neural network then predicts these two things. And it's going to ask, what is this? What is this? And I'm going to ask you that too. What are these? Like, what should they be? In our BERT, we knew what the output should be. It went with this. But these two things kind of go with this continuous signal. Here, it's not obvious. There's not like this nice one-to-one relationship of what it should be. And this is the problem we face with mass language modeling on our audio. And this is essentially what Wav2Vec solves. They do it in a very creative way, and we'll show how they do it today. So that's basically what we'll be exploring. There's a bunch of steps that go into this. So let's erase all U. And so let's go down. So Wav2Vec is essentially a model that's trained in a couple of different ways. First, it does a contrastive task over quantized latent representations. And these quantized representations are jointly learned. And all of these things are really important. And we're going to explore each piece of this as we go. And so let's go ahead and start from here. The approach encodes speech audio via multi-layer convolutional neural networks and then mask spans the resulting latent speech representations similar to mass language modeling. So we'll be looking at the masking method in just a bit. After that, the latent representations are fed to a transformer network, and the model is trained via contrastive task, where the true latent is being distinguished from distractors. So let's go ahead and see what that looks like. So let's just draw it out. So what we're going to do is in Wav2Vec, and maybe we can actually look at the original figure, and we'll kind of base off of this. What we're going to do is we'll take some audio, and we're going to train some convolutions on it, and we're going to extract some features Z1, Z2, Z3, Z4, Z5. So let's do that. So we're going to extract, and let's do this in the colors that they are, just so it's clear. We'll have a Z1, Z2, Z3, Z4, Z5. So these are my outputs, Z1, Z2, Z3, Z4, Z5. These are the outputs of my convolution. Now, what I need is a target, because again, if I just, like I done earlier, if I just randomly mask out, in this case, they select this one to be masked, as you can see. If I randomly mask it out, the question is, what is this? What should this be? And there isn't a good answer of what it should be because we don't have a target. It came from some continuous audio. And so because we don't have a target, we can't just do simple mass language modeling. So can we create a target? Yeah, of course we can. We can use something known as quantization. So let's talk about why this is jointly trained, or what makes it unique that it's jointly trained, because this whole process used to actually be a two-step process. So let's do it this way. Our goal is to create some discrete representations of audio, right? Some discrete, just like how in text we have discrete tokens, we want to have discrete representations of our audio. So we need to train something known as a speech, or audio, tokenizer, right? So this is something that takes a waveform like this, and it'll look kind of like a VQVAE, right? So this is essentially a VQVAE model, VQVAE. We have this. We're gonna an encoder will have a codebook, and then we have a decoder, right? Standard VQVAE setup. So if you don't know anything about VQVAE, I also have a video on that, which I'll link down below. So go ahead and watch that. But the VQVAE does that. It essentially discretizes your audio, and we'll have the reconstruction task on the other end. So we pass in audio, we go ahead and learn some quantized latent representations, right? Which is going to be, if there's k possible codes in the codebook, then it'll be each of these have to be one of those k things. And then we have a decoder that reconstructs the audio from these quantized embeddings. And of course, VQVAE has its limitations, which is why this paper doesn't use it. So we'll talk about that in just a second. But for now, that's the main idea. We take audio and we quantize it. And so what you end up with is something like this, a quantization module. You'll get audio, and you can map it to some numbers, some tokens, 2, 7, 3, 5, 11, ... whatever. Some discrete tokens that identify the index, right? That this is the index. So this was the second thing from our codebook. Then it was the 7th thing from the codebook, the 3rd thing from the codebook, ... So we go ahead and discretize it, and now we can train a mass language model on these discrete tokens here, right? Basically do what BERT does by just training it on these tokens here, and this tokenizer was created from our speech tokenizer. No problem. But this is and so we'll pass this to a masked language model. So stage 1 is train the speech tokenizer. Stage 2, train a masked language model on those speech tokens. This, although kind of cool in practice, is probably less good than training a single end-to-end model. And so when Wav2Vec says that we can train a latent space and quantized representations jointly, this is exactly what it's talking about. It avoids doing this 2-stage problem. So let's go ahead and get rid of you because we don't want to do 2 stages. Here we go. If you want to learn more about speech quantization, you can look at the Encoder paper and some other papers that explore a lot of really cool ways of doing that. So that's what it means by jointly. It is a jointly learned representation. So that's the first thing. So what we do is we take each of these continuous vectors, right? These are z's, right? Z's, and we predict some quantized vector that represents them. So the q's here, quantized, are from a set of possible codes. And we'll talk about exactly how the quantization happens in a bit. But for now, let's just do that. We have, basically, we produce these q's. And this will be q1, q2, q3, q4, q5, right? So each of our continuous embeddings are mapped to one of, let's say, k possible quantized codes, right? So there's k possibilities here. Now that we have that, we have a target. We have a target that we can use. Again, remember in BERT, we had a target. We knew exactly what this thing could be. It could be one of many quantized, not quantized, but one of many discrete tokens. And so what we've done is discretize it. We only have, however, let's say k, we only have k possibilities of codes here. And so this has to be one of k things. So we've created these quantized vectors, and we're going to just keep them on the side for now. We're going to keep them on the side for now. After we've completed quantization, then we're going to go ahead and select something to mask. So they mask the 3rd thing, so we're going to go ahead and mask you. So you're going to be masked, and we're going to pass this to our transformer, right? We're going to pass this mask data to the transformer, and we're going to get some output that's going to say, what is this? What should this thing be? And we know exactly what it should be. It should be Q3, right? That's the quantized representation that it maps to. So this, basically this embedding, the output context vector, and this quantized vector go together. And that's the key idea. So we've essentially created, and the way I like to think about it, is these quantized vectors is kind of like our speech or audio vocabulary, right? Vocabulary. Just like in a tokenizer, you have your the vocabulary of your tokenizer, we have the vocabulary of our audio. It's just in this neural network, what makes it unique is instead of training a speech tokenizer first and then training a mass language model on top of that on top of those speech tokens, go ahead and train the whole thing at once. We have our speech tokens at the beginning and the mass language on that. And the intuition is that these convolutions are extracting acoustic features from our audio. So these quantized representations are just a representation of raw acoustic features that come from the audio. And our neural network's goal is to predict, given some missing information, what is the acoustic feature that should have been here, given the context of all the other features, right? That's the main idea. Now, how it does this exactly is a little bit more complicated. So let's go ahead and start digging into some of the pieces here. The first step, of course, is our feature encoder, right? Feature encoder. This is, as it says, it's just a bunch of convolutions with a layer norm, GLU activation, and the only pre-processing they do to the audio is they just normalize each audio individually to be zero mean unit variance. So this can be in our data loader or data collation function when we write it later. But that's no problem. That is our feature encoder. Now, of course, just like every transformer, we need to add positional information, right? We need to add positional information to our data. And otherwise, a transformer doesn't know how one time step is related to another time step because transformers are permutation invariant. So there's a bunch of options for positional information. There's sine, cosine embeddings. There's our learned embeddings. And neither of these are very helpful. Sine, cosine probably still would work, but learned embeddings would not. So learned embeddings, how they work is we'll have some sequence length by embedding dim, and we'll have some embedding here that represents each position, and this is learned just like everything else. The problem with learned embeddings is it limits our length of the sequence, right? We can't, if we set S to 1,000, then we can't work with audios that when encoded, right? So the output of the convolution is longer than 1,000. That's a little bit restrictive in audio when it's pretty dynamic, and the length of audio can change pretty drastically depending on what you're working on. So instead, they decide to use relative positional embeddings using a convolution layer. So how this works out is they have some, let's say we have these outputs of our convolution. So after that feature encoder module, we have some outputs here. And this is going to go to a convolution, some convolution, and then the output of this is going to be added back to here. So we're adding positional information in, but it's relative. Now, why would it be relative position information? That's because when we have embeddings, right, how do 1D convolutions work? 1D convolutions have some kernel size. Let's say we have a kernel size of 3. So what we're going to do is convolve over this, and it'll look at, let's say, the first 3 things. And then the output of that will be added back in. And then we're going to look at the next 3 things. Output of that's going to be added back in. The next 3 things. Output of that's going to be added back in. And so the model really just sees the the center thing and the neighboring tokens. And depending on the kernel size, if you have a kernel size of 5, then it would be like all of this. So depending on the kernel length, that's a little bit important. But it looks at the center, looks at the neighbor, and it encodes that information into here. So this model kind of sees what's near it, and so it's a relative positional information because it just sees what's near it rather than globally across the entire context. But this is pretty fine because speech is relatively local, right? Like when I'm speaking, the way I say something in one word doesn't really affect how I may say something many, many words later. So having full global positional information may just be overkill or redundant, so we go with this. In more modern architectures today, like Parakeet or whatnot, they use more advanced positional information methods like rotary embeddings and stuff like that. But for now, we're going to stick to this. So it's just a simple convolution layer, nothing else. After that, we have our quantization module, and this is essentially the heart of our architecture. And so we're going to spend a little bit of time here just understanding what's going on and to understand some of the limitations of existing quantization methods and why they went with this way. So in quantization, the setup is typically like this, right? You have some embeddings and you want to map it to some code book, right? With K codes in it, right? And each code has some embedding dim. That's fine. The problem with this setup is, what should K be? In speech, Speech is a pretty high variance data set, right? Even if everyone is saying exactly the same thing, it's still very different depending on how someone's saying it. And so speech is a high variance data set, which means if we want quantized vectors, right, that can represent the diversity of speech, because again, our entire architecture depends on the quality of these quantized vectors, because our transformer is going to be learning how the output is related to the initial quantization. So if my quantizations are garbage, then the model will be learning garbage representations. That's basically the main idea. And so we need our quantization module to be able to have the capacity to learn a large variety of information. And so here's where the problem becomes. As k becomes large, let's say we set k to 50,000, right? 50,000, which isn't even that much. Our neural network will, and like most VQVAE type methods, you'll most likely face something called index collapse, where you have all these codes, but the model just kind of uses some of them, but ignores the other one, like just doesn't care about some of them. And this is a bit of a problem, right? Because if we want our model to actually express a large variety of acoustic features, then we need it to actually utilize a large codebook. It's just getting a neural network to use a large codebook is a problem. We can add some things to help to it, and this model does it too, despite using smaller codebooks. We add something called perplexity loss, or in this paper they call it the diversity loss. But regardless, it's definitely a struggle to get a neural network to actually use and explore an entire large codebook. And so what do? This paper opts to do something unique and different. It uses multiple codebooks and then concatenates them. Okay, why does that work? Let's say instead of having one giant codebook with 100,000 vectors, right, which would be very hard for a neural network to explore, let's go ahead and just have two different codebooks, each with 100 vectors. So we have codebook 1, codebook 2. This has 100 vectors here. We have some embedding, right? And we want to quantize it. And what we're going to do is look at the first codebook and select a code that we want from the first codebook. And then this vector is going to look at the second codebook, select a code that it wants from the second codebook. And then we're going to grab both of these codes and concatenate them together. The reason concatenating is important is because we have 100 possibilities in the first thing, 100 possibilities in the second thing, which means if we concatenate things together, there are 100 squared, or 10,000 possibilities, right? And if we increase our number of codes in each codebook, then we'll end up increasing the number of possibilities quadratically, right? So if we pick, instead of 100, if we pick 200, then we'll end up with like 40,000 or something like that. So it's very nice, right? Very nice to do it this way, because we effectively get lots of different unique quantizations by doing all the possible combinations of smaller codebooks. And small codebooks are easier to explore. So this is a key idea, and that's how they define it here, right? So they have G different codebooks, which in the implementation they set to 2, and then V different entries. Each codebook, I think, had 320 different possible codes. We choose one entry from each codebook and then concatenate the resulting vectors. And so that's the key idea. And then they do a linear projection of that concatenated vector. Now, here's one key step. How do you choose a vector? How do we choose the code? Well, in VQVAE, right, in VQVAE, they use MSE, right? They do argmin of the Euclidean distance, right? So L2 distance. They do argmin. So they take this code, they take our code, they look at every single code in this codebook, and then they find the one that has the closest Euclidean distance. Okay, fine. But this argmin is not differentiable, right? It's not differentiable, which is why VQVAEs have all this extra stuff. We have a codebook loss and a commitment loss. And this helps us actually train our model, train the codebooks because without that, the codebook would never get gradients because argmin is not a differentiable operation. Because we end up using a straight through estimator, skipping around this non-differentiability, and then we use these two as our best guess to give derivative information, gradient information to our codebook so they can actually train. And so this is obviously a unstable way of training, probably not good, especially for a model like this where there's just so much stuff going on. Wav2Vec is a relatively unstable model to train and requires a little bit of help. And so if we can't do VQVAE in the standard way, where we do mean squared error between this and this, and this and this, then we'd end up with 2 different codebook losses, 1 per codebook, and 2 different commitment losses, 1 per codebook. If we want to avoid that, how do we do it? They opt to use something called the Gumbel Softmax. So I just made a video detailing everything about Gumbel Softmax from its derivations, what is the Gumbel distribution, stuff like that. So you can go ahead and take a look at that if you want some more details, but I'll just give the high-level idea here. What if we treat our selection of the codebook as a sampling problem, rather than as a selection problem, kind of like a sampling problem? So let's kind of do it this way. We have an embedding vector here. We can train a linear layer that goes from whatever the dimension of this is to 100. Why 100? Because I have 100 code vectors here. So the neural network will output some logits, right? Like -2, 4, -8, 3, 7, 2, ... Right? We'll have some raw logits that come out of our layer. And then we want to select from here, we want to sample from this distribution. So obviously we can do a softmax, right? We can take a softmax of this and then do the argmax to get the most likely. What is the most likely one? Or we can do like a multinomial sampling, right? So we can, we'll end up getting a distribution of the probability that we should pick quantized 1 is like 0.2. The probability of selecting quantized 2 is like 0.1, ... And then we can use multinomial sampling to sample from this and then select that code and keep going. Problem is sampling, right? Sampling from a distribution, like multinomial sampling, is not differentiable. You can't take the derivative of a sampling operation. And so Gumbel Softmax is a categorical reparameterization of sampling, which is really cool. So Gumbel Softmax essentially allows us to sample from this distribution without actually sampling from it. And the way it does it is we take our raw logits, and so the original Gumbel max trick basically takes raw logits, adds some Gumbel noise to it, which is a distribution, Gumbel, and it'll be Gumbel 01, so standard Gumbel noise, and we'll do the arg max of this, right? The arg max of this. And it turns out that, and this is the derivation that I do in that video, so if you're interested, go watch it. It turns out that doing this gives you effectively the same process, the same distribution as if you had taken the softmax and then done multinomial sampling. So if doing softmax plus multinomial sampling shows that, 20% of the time I pick Q1, 10% of the time I pick Q2. If you do it this way, then again, you're going to get roughly the same thing. 20% of the time you'll pick the first code, 10% of the time you'll pick the second code, ... And again, if you don't believe that, you can go watch that video. Now, argmax, again, is not a differentiable operation, so that's why instead of doing Gumbel max, we do Gumbel softmax, which does exactly the same thing. We're going to do our raw logit plus Gumbel noise, which you can see is here. This is our Gumbel noise. And we do e to the power that divided by sum over everything else. So that's standard softmax. But what you see here is this temperature parameter. And the temperature parameter is how we kind of deal with our Gumbel max versus Gumbel softmax. Because Gumbel max is not differentiable, and Gumbel softmax is essentially a soft operation of doing exactly the same thing. So tau is a temperature parameter that allows us, when large, it allows us to cool our probabilities. So when tau is large, the distribution over all of the embeddings here will be close to uniform. So all embeddings, all quantized vectors will be pretty likely to be selected, right? Uniform. So they'll all be about the same likelihood to pick them. As tau gets smaller and smaller, our distribution gets sharper and sharper, and our model will give more probability to a specific code and less probability to all the other codes. This is kind of helpful in a couple different ways because, first of all, when we're training anyway, at the beginning of training, it's not like our model it knows anything about these codes. These codes have no gradient information. There's nothing there. And so if our model's kind of being a little bit more random in what code it's selecting due to the higher temperature, That's probably a good thing, right? It'll allow it to explore the codebook a bit more. But as the model gets better and better, you want it to actually commit to a code rather than just randomly selecting, right? It should actually select something that's good rather than being random. And so as tau gets smaller and smaller, the model's forced to commit more and more to that. And so that's the main idea. We're able to do this, and the best part about all of this is a fully differentiable operation. This is essentially the reparameterization trick that we did in the variational autoencoder. We just have some outputs and we're adding some noise to it. In variational autoencoders, we're adding Gaussian noise, but in this case, we're adding Gumbel noise. But the same idea, it's just a reparameterization trick. So again, if you want to know more details on this, just go ahead and watch that video where we go into the derivation of why all this works. But that's essentially the idea. And the reason it's differentiable is because during the forward pass, we get the index that we wanted, but in the backward pass, the true gradient, right, the true gradient of the Softmax output is used. And we derive the soft versus hard version of Gumbel Softmax as well in that video. So go ahead and watch that again. Now that we have this, we have a way of selecting codes in a differentiable manner. So notice there's no more codebook loss, no commitment loss, none of that stuff. Very simple. Because we have all that ready to go, we now have quantized embeddings. And we have a large variety of quantized embeddings because we have 2 codebooks. So this would be 100 squared possible codes, right, between the 2 after concatenating. So that takes care of this first step. How do I quantize my audio to get some targets? Next part is, how do I train with these things? So let's go ahead and take a look. So during training, the first step is our masking procedure. And so here's one interesting thing when it comes to masking. When you have audio has a pretty strong autocorrelation, right? Pretty strong autocorrelation. And the thing is that when we're randomly masking, let's say we randomly select to mask this thing here, and we want to predict it, there's a huge overlap in the convolution, the receptive fields of the convolution between this thing, and then that center one. And that's a little bit of a problem because that makes it's too easy, right? If there's a huge relation between neighboring tokens, then the model will just kind of learn to copy information from the neighboring tokens into here. And that's just too simple of a problem. And so the way we typically do this for speech is something known as span masking. Instead of just like BERT, where we kind of randomly mask 15% of the tokens, what we do is we mask out entire spans of tokens. So like it'll have to use everything else to predict like an entire span worth of token. And it doesn't have that internal context to predict the neighboring thing. So that's the main benefit of span masking, why it's important for something like this. So the way they do this is they randomly select. So we'll have all of these, let's say all of these embeddings, right? We'll have, let's just try it like this, all of these embeddings. We're going to randomly select with p proportion some of these embeddings. Let's say we select this one, and it's a relatively small percent. I think it's like 5% or something like that. So you select something like that. And then you go ahead and mask out m subsequent consecutive steps. So we'll mask it. If we pick 3, then we'll predict or mask out all 3 of these things. And then we'll mask out all 3 of these things. And then we'll mask out all 3 of these things. Something like that. And our neural network has to use only the available information around these kind of large spans to fill them in. And so this is much more challenging for the purposes of audio because there's so much autocorrelation in audio that neighboring convolutions would make it too easy. If we had done the standard BERT procedure where we just randomly mask 15%, then it would have ended up being something kind of like something like this. Let's put this one back here. If we had just like randomly masked, here we go, right here. Okay, if we had just kind of randomly masked 15% of the things, well, this thing can be easily predicted by this and this, and this thing can be easily predicted by this and this, and this can be easily predicted by this and this, ... Right? So that's too easy of a task, right? And the model will just end up learning to copy neighboring information over, which is why, again, we decide to do span masking, right? So span masking. So that's the entire setup. And so now what is the objective for training? There's going to be 2 different tasks happening. The contrastive task, and then also a diversity loss, all right? And diversity loss is to encourage the model to use codebook entries equally often. And we'll see how that works out in a bit. So let's start with the contrastive task. Let's actually draw this out because it'll make it a little bit easier to understand. What is our setup? What we have is a bunch of, let's say we have our z's. So those were blue. So let's do it in blue again. We have z1, z2, z3, z4, z5, z6, z7. Let's just do that. So these were our z's, right? These are the continuous outputs of our convolution, right? So the convolution produced these. And then we go ahead and quantize all of them, right? So Q1, Q2, Q3, Q4, Q5, Q6, Q7. So these are my quantized embeddings. And then what I do is I go ahead and randomly mask a span of them, right? But let's just do one of them now, just for simplicity. We're going to randomly, let's say we select this one to mask. We'll mask more, but let's just do one. And this is going to pass to a transformer, right? Transformer. And we're going to get some output context vectors. C1, C2, C3, C4, C5, C6, C7. And so these are our output context vectors from our transformer. And so our goal is to predict, again, remember, this vector, this context vector, is the one that was initially masked. And so that's the one we're asking about. And so we know the answer is this here. This is the corresponding quantized token that's correct. But whenever you train neural networks, you typically, and anything, you need positive samples, the correct answer, and negative samples, the incorrect answer, right? So we can set it up exactly like that. So what we're going to do is set it up like this. We're going to grab, and I'll give it labels this time. We have context 3, right? So this is context 3. And context 3 definitely goes with this one here, quantized 3. But we need some negative samples. So this is the correct answer. So what if I randomly sample some other ones as negative? So let's say I randomly sample U, and let's use a different color for the negatives. Let's do green. Let's say I sample these for the negatives. So we have quantized 1, quantized 2, so quantized 2, and then 2, 3, 4, 5, 6. So quantized 6. So these are my negatives, and this is my positive. And our neural network's goal is to take context 3, the output of the mask token, right? So whatever the mask token was, its goal is to minimize the distance to this and maximize it to everything else, right? These are not good pairs. These are incorrect pairs, but this is the correct pair. And so so these 3 are incorrect pairs. And then this one is the correct one. And that's the main idea, right? So that's how we set up, and this is honestly the hardest, most annoying part of the implementation for Wav2Vec, setting up this entire sampling process. We're going to spend more time on our data than we will on writing the model. The model is relatively simple, but regardless, this is essentially the setup, right? This is exactly what we're going to do. We're going to take our code vector. We are going to grab the position for our context vector for what was masked, and then for each of these, we're going to sample, we're going to have the correct answer, and then we're going to sample k more incorrect answers, right? The quantized tokens they don't go with. And then we do a simple contrastive loss. Contrastive loss is minimize the cosine distance or cosine similarity between my C3 and my Q3, the correct answer, and maximize it to C3 and Q1, Q2, Q6, and anything else. So in the end here, we will have k will have 1 correct answer plus k incorrect answer. So this will be we'll have 1 plus k things in here. And that's the main idea. So let's go ahead and return back to here. We have our contrastive loss. So here we go. So as you can see, we have essentially, there will be k plus 1 quantized candidate representations, which includes k distractors or negative samples, right? And then we have 1 positive sample, right? The correct answer for that time step. And these distractors, right? Distractors are uniformly sampled from all other mask time steps. So we'll have all those quantized embeddings. We'll just randomly pick them, right? We'll randomly pick them. And when you have multiple of them, you'll have multiple of them. So in the case here, let's say we had masked, we did span masking, right? So we masked these three things. So which means we had C3, C4, and C5 were all selected to be masked. And so we want to train C3 to map, C3 should map to Q3. And it should have some negative, and we'll randomly sample from all of the other Qs that is not Q3. We're going to sample from Q where Qi, where I not equal to 3. So we're going to sample from all the Qs that's not 3. Again, C4 should map to Q4. And then our negatives will be sample from Qi, where I not equal to 4, right? Everything that isn't the correct corresponding quantized token is the one that we'll sample as our negatives, and we will uniformly sample, right? Any one of them is fair game. And so now that we have all of that, that's essentially our diversity, our contrastive loss, right? So we're gonna, and the way they set it up is we have our similarity. This is cosine similarity, and we're going to compute the cosine similarity between our CT and all other QTs, right? So QT is the correct answer, but then Q tilde is all the other Qs. So there you go. Compute them. And then because we're going to be using cross entropy to set this up, we want to maximize the similarity of the correct answer and minimize it to everything else. We essentially just do standard cross entropy loss here, right, on that. And the cross entropy is applied on cosine similarity distance rather than standard like probability measures and stuff like that. So there we go. We now have that. And we also add this additional thing here, kappa. Kappa is just set to 0.1 in this paper. It's just a temperature parameter to help like sharpen the distribution a little bit. So there we go. And so that's it. So we're just doing simple cosine similarity between context representations and quantized latent speech representations, where we have k distractors and one true answer. And you'll see how we implement that. It's relative. This part is not too bad. After that, we have the diversity loss. So even though we have relatively small code books, so I think in the final implementation, we'll have 320 code books per code book, right? So if there are 320 codes per code book, we want to make sure that the model's actually using all the code books, right? Because even in small code books, you could have index collapse, just like you do in VQVAE. So we have a diversity loss that's going to be motivating the model to use a little bit more. So how do we exactly do this? This is essentially the formula for it. We're going to be maximizing our entropy. So let's kind of see how this works out. Let's say we have a code book, right? We have a code book here. Code book. And it has all these codes. There's k codes in it. Let's just pretend we have one code book right now, just for simplicity. And let's say our first, and of course we train in batches, right? For batches, but let's say we have a batch size of 3, right? Batch size is 3. So, and the first batch will have its, outputs that need to be quantized. The second batch will have its outputs that need to be quantized. And the third batch will have its outputs that need to be quantized. And so now the question is, what are the quantized vectors that they get? So we can first quantize the first one. Let's just pretend all of these batches kind of end up quantizing like this. So let's say they pick let's say these 4 just get mapped to 3. So one of them is reusing the same quantization. And then the second one is using, let's say, 2 of the same ones and maybe another one. And then the third one is using, again, 2 of the same ones. And let's say it overlaps with this too. So across this batch, this codebook looks relatively unutilized, right? Unutilized, because almost everything is just using kind of these handful of codes here. And this is standard index collapse, right? Where your model is not leveraging all of the available codes. And so in this situation, what we do is we compute what proportion of our codebook was utilized. And if it's not utilizing the entire codebook, then we're not doing so well. And the way they do this is through maximizing entropy. So what we do here is, and let's just read it, we encourage the equal use of V entries in each of the G codebooks by maximizing entropy of the average softmax distribution over the codebook entries for each codebook across a batch of utterances. The softmax distribution does not contain Gumbel noise nor temperature. So that part is fine. And let's just look at the formula. basically, we can compute what was the probability of the model selecting a code, right? We know what the likelihood of a model selecting a code is because we have data. We can see which codes were used and which codes were not used. And so we know the probability of a specific code being selected because we can compute that. And that's basically what this is, the probability of a code being selected. Now, if every code was equally likely to be selected, and let's ignore the G right now. G is across codebooks. Let's just look at a single codebook. If every code is equally likely to be selected, and there's k codes, that means the probability of selecting a code, any one of the codes, would be 1 over k, because it's uniform, right? It's random. And 1 over k would mean every code is equally likely. So what is the sum? And let's use v actually for the notation, because they use v, so 1 over v. We're going to do the sum of 1 over v log 1 over v. And they actually do, yeah, that should be fine. And then we'll get v equals 1 to big V, just like that. Well, let's go ahead and this, let's actually make this a little bit clearer. Let's say I equals 1 to v, because this v here is a constant. That's the probability. This v here is a constant. So everything here is a constant, right? Everything here is a constant, which means this will end up being 1 over v. It'll really be v times 1 over v times log 1 over v, which is just negative, right? Negative log v. These two things will cancel, and so we'll be left with the negative log v. And this is the negative entropy. As you can see, they put a negative sign at the beginning. The entropy, if we didn't take the negative sign, would have been log v. And log v is actually the maximum entropy you can have, and this is the entropy of a uniform distribution. So our goal, our final goal, is to make sure that our codebook is somewhat uniformly selected. The closer we can get to every single code being equally likely, 1 over v, to be selected, the closer we are to maximum entropy. So this part here is essentially computing, because we want to minimize, right? Because we don't maximize. So we want to maximize log v or minimize our negative of it. So this should end up as log v at the end if our model does everything correctly. And then we're going to sum it up for everything. And that's it. We're just going to add it up to add up for all the different codebooks, and then just average it out for between all the codes and all the codebooks and that sort of stuff. So there's really nothing crazy happening here. It's really just a metric for that. Now, funny enough, they don't actually use this method. They use this little subtext right here. So let's just dig into that real quick. We have this gv minus some e to the power negative something happening. So let's just pull it apart. Instead of maximizing entropy, they maximize perplexity, but it's the same thing. So they have gv minus, we have that sum over our codebooks again, which I'll just write like this, e to the power negative sum over our codes for each codebook, and we have p times log p. And these p's are the same thing, and we divide by gv. Well, how does this work out? We know that in a perfect uniform distribution, this should end up as log v, right? Log v. So this will end up as log v, or negative log v in our case, right? Because we saw above, right here, this ended up being, this entire operation ended up being negative log v. So we have a negative log v times this negative 1 right here. So that'll just be a log v. And e to the power log v is, well, e to the power something is v, so e to the power of that is just v. So this is just equal to gv minus g, or sum over g, right? G codebooks. And these will just be v, right? E to the power log v is just v. And then we're going to divide by gv. Oh, gv. And then the sum of v, g times, is just gv. So this ends up just being 0 over gv, which is just 0. So we can see that by maximizing perplexity, we're essentially minimizing this thing. So as long as our final distribution of selecting each code is 1 over v, then it's close to uniform, and uniform maximizes entropy, or it minimizes this loss, right? Because in the end, we're minimizing stuff, not maximizing. So this is the actual implementation that we're going to be using, right? It's a little bit more stable because we essentially get rid of this log operation, right? So a little bit more stable. But this is exactly the same thing, right? It's just two different ways of doing it, but they give the same result. And so that is our diversity loss. Again, the diversity loss just ensures that we're using a variety of the codes. Because again, remember, if our quantization module is garbage, and let's say all the queues end up mapping to the exact same code or just a couple of different codes, because our model just is not extracting a diverse enough features, and our quantizations of those things are just also not very varied, then our transformer only has to predict the handful of codes that it gets. So it becomes, again, a very simple problem. So the only way for our transformer to actually struggle to learn this representation is by having strong quantizations here. And so again, that's what makes Wav2Vec so cool, because all of this has to be trained end to end. Finally, right, once we're done with all this pre-training, so you pre-train this model, and once you're done pre-training, then you can fine-tune it, right? We basically have a model that takes in audio, just like we had with our deep speech 2. It takes in audio. We won't have any mouse spectrograms, so that's why it's called Wav2Vec, because we're going to be working on our wave files directly, right? We'll be working on the audio files, waveforms directly. There's no intermediate representation that we use. We're going to go ahead and we have a transformer, some convolutions and transformers that process it. We get some outputs, and we can do some CTC loss, just like before, to do our actual transcription task. It's just that we need, because we pre-trained this model already and it understands the acoustic features of speech, this CTC task requires significantly less data than the nearly 1,000 hours we need to get reasonable performance on something like deep speech 2. And so that's the main idea, right? So we've kind of covered all the main things here. There are a couple of extra things that we can talk about right here. So for pre-training, just to give some ideas, they use, so each token is predicted as p equals 0.065, and then every token that's selected, they go ahead and do a span of 10. So they'll select that token and then the next 10 after that. And this leads to roughly about 50% of the data being masked out, right? So about half your output is masked and the other half isn't. They provide some information here about the convolutions that we have, and it looks like after doing these convolutions, every single embedding, so after the convolutions, you'll get embeddings, right? Embeddings. Each of them will have about 49 hertz worth of audio, right? So that's the output frequency, with about 20 milliseconds worth of layer. So we get about 25 milliseconds of audio with 20 milliseconds between each sample. And this is what I meant by the problem being challenging. If we have two embeddings, and this one represents 25 milliseconds worth of audio, but then there's a and then this one, and then we move over by 20. So essentially the last 5 milliseconds and then the next 25 or whatever, or 20. Let's actually draw this out a little bit better. Let's be clear. We have some audio here, and the first convolution is going to extract 20 milliseconds of, or 25 milliseconds of audio, 25. But the next convolution will have 5 milliseconds of this and onwards, right? So 25 more. So there's an overlap between these convolutions. Would make sense. There's always an overlap between convolutions when we set it up, because we do like a, even with a larger stride, with these larger kernels, it ends up having some overlap between every convolution. And so with this final output, we end up having a overlap between the two, which means if we do standard masking like BERT, there's so much overlap between a token and its neighboring tokens that would be too easy of a problem to solve, which is why span masking is so important, to make it not trivial, right? That's the entire idea. We want to make it a difficult problem for the model to solve. The other thing is the convolution layer to do relative positional embeddings. It's not just a normal convolution, it's a grouped convolution. So we'll have a grouped convolution layer there as well. After that, they have a standard setup for most of this stuff. It's a 12 transformer blocks. They opt to have 8 attention heads, but I think their posted implementation is 12 attention heads. They use an embedding of 768, and each sample is about, looks like on average about 15.6 seconds. We'll set all this up for our data set. It'll be fine. And their batch size is roughly about 1.4 minutes per batch, right? So we'll see again 1.6 hours per batch. which is a huge batch size, which we will not be able to meet without having 64 V100s lying around. And they're able to train in 1.6 days, where my reproduction took about 8-9 days to get not even as good performance, but that's all right. This is all for learning. So we'll kind of set up all of this stuff later. Again, the Gumbel Softmax, it has that temperature parameter, which cools the distribution, or cools our sampling for those quantization, and they anneal it from 2 to 0.5 for the base model. So we'll be doing the same thing. And then that kappa, the temperature parameter on our contrastive loss, is just set to a constant of 0.1, but that also may not necessarily be the best way. Modern models, modern architectures like CLIP and stuff like that use like a learnable temperature parameter as well. So that's another option. And then the last thing is when we select for a specific code, we have specific output, masked output, we have the correct quantization module, or the correct quantized embedding, and then we need to randomly sample k other quantized distractors, and they select k equals 100, right? So we'll be doing the same thing, k equals 100. And fine-tuning is relatively simple. We'll be just doing a simple CTC loss fine-tuning on that. And so that kind of covers all of the main takeaways of this paper. The coolest part is mainly this. We get really great results on very tiny amounts of data. So you can see just on 10 minutes of labeled data, we still get great results. Especially on the larger models, we get even better results on these things. So that's great to see that it kind of works out so well on limited data sets, because that's the entire point of pre-training. Pre-train on lots and lots and lots of data, so the model picks up interesting acoustic features, and then fine-tune on the limited set of data that you actually care about. And that's the standard paradigm for most training these days. Other than that, I mean, you can go through the results here. There isn't too much more. These are essentially ablation studies. They also we're going to be doing CTC on characters, transcripts. You can also do it on phoneme recognition. That would be another totally fine way of doing it. So you'd need audio phoneme pairs like Timit provides, a bunch of citations, and yeah, these are just a bunch of ablation studies. So again, that's basically the main idea. We took the two-stage process of first training a speech tokenizer, and then training a language model, a mass language model on top of that. We converted that to a single end-to-end model that does all of it. And the toughest part of our implementation will be setting up this right here, the sampling, the entire selection of k+1, wherever it was. The selection of k different quantized embeddings is the most annoying code that we're going to be writing, but it's going to be okay. We're going to get through it just fine. So I'm going to call it here. Again, this was just to give you a brief idea of Wav2Vec. We'll be referring back to this paper as we're implementing it, just so you can see those relations between the implementation and the paper itself. So I will see y'all in the next one.